Dynamic programming is one of the most powerful algorithmic techniques in computer science. The basic premise centers around the idea of solving a problem by first identifying and solving subproblems, and then bringing these subproblems together in some manner to solve the larger problem. Not surprisingly, this process is easier said than done. In fact, dynamic programming problems can be notoriously challenging to wrap your head around. In this video, I'll walk you through 5 steps that you can use to help tackle dynamic programming problems and show you how they work in the context of 2 specific problems. The first problem is a pretty fundamental one, while the second one is a more challenging extension. And at the end of this video, we'll have a discussion of general approaches to dynamic programming beyond the examples in this video. Let's get started. The first example we'll look at is the longest increasing subsequence problem. Let's say you're given a sequence of n elements and you want to find the length of the longest increasing subsequence. An increasing subsequence is just a sequence of elements where each subsequent element has both a larger value and index than the previous element. Here are some examples to clarify what I mean here. Given the following sequence, the longest increasing subsequence is 1, followed by 2, followed by 5, with a total length of 3. Now that the problem is more clear, take a second to see if you can find the longest increasing subsequence and its respective length for the following sequence. The correct subsequence starts at 2, followed by 3, 6, and 9, with a total length of 4. Now, one important note for this problem is that to keep things simple for now, we will focus on finding the length of the sequence rather than finding the sequence itself. The first step in solving dynamic programming problems is to find a way to visualize examples. Visualization is a great way to see connections and underlying patterns in the problem that can later be relevant to the solution. When solving this particular problem, we clearly have some restrictions on valid sequences, so it makes sense to find a way to diagram out what makes a valid sequence. A nice model that shows up all the time in dynamic programming is the directed acyclic graph. Imagine each element of the sequence is a node in a graph, and we construct a directed edge from one node to another if the node on the right contains a larger value. Here's what the directed acyclic graph representation looks like for this particular input sequence. What's nice about this representation is that an increasing subsequence is just another path in the graph. In fact, going one step deeper, the length of the longest increasing subsequence corresponds to the length of the longest path in this directed acyclic graph plus 1, since we are technically counting nodes. Solving this particular problem might be a little bit more clear, and sometimes this shift in perspective is the key to making challenging problems more approachable. The next step for solving a dynamic programming problem is to find an appropriate subproblem. A subproblem is basically a simpler version of our overall problem. Finding subproblems can be tricky, but let's focus on what we know about this problem. We know the longest increasing subsequence is going to be a particular subset of our initial sequence. One way to specify this subset is through the starting point and the ending point. Every increasing subsequence, no matter how long, will have a starting and ending point within the original sequence. So let's modify one of these variables to create a subproblem. Turns out that you can solve this particular problem with either choice, but I personally find focusing on the ending point of a subsequence as a little bit more intuitive. Let's define a subproblem for the sequence as LIS at index k, which would mean the longest increasing subsequence ending at index k. For example, the LIS ending at 3 would be the sequence starting at 1, followed by 2, which has a length of 2. Remember that when I am referring to LIS in this particular problem, it is specifically with respect to the length of the sequence. Okay, so now that we've identified one possible subproblem, the third step requires finding relationships among subproblems. It often helps to ask yourself questions in this phase. For example, suppose you want to solve the subproblem of finding the longest increasing subsequence ending at index 4. What subproblems are necessary to solve this? Well, the nice thing about this graphical visualization is that it makes it quite clear what subproblems we need. One path through index 4 must go through index 0, so we will need to know the length of the longest increasing subsequence ending at index 0, which happens to be 1. Another path comes through index 1, so we'll need that subproblem as well, which also has length 1. The final possible path ending at index 4 goes through index 3, and the longest increasing subsequence ending at index 3 has length 2. Now the nice relationship here is that the length of the longest increasing subsequence is just going to be 1 plus the max over all the necessary subproblems, which ends up being 3. And this should intuitively make sense, right? If I want to find the longest increasing subsequence ending at index 4, it does make sense that I would just add 1 to the longest increasing subsequence over all subsequences that eventually arrive at index 4. So once you've found a reasonable relationship among subproblems, we want to then generalize this relationship. Let's look at our other example and see if we can come up with a similar process to solve the longest increasing subsequence ending at index 5. The key idea here is that we're going to choose subproblems ending at index k if and only if k is less than 5 and the value at index k is less than the value at index 5. Seeing this relationship in action, we start at k equals 0, and since the value at index 0 is less than 6, we need to know the answers to this subproblem. And we continue to go through all possible k values less than 5 and include subproblems that satisfy the constraints laid out by the problem. And in reality, there's nothing special about index 5. This applies for any n, so the general relationship for finding the solution to a subproblem of the longest increasing subsequence ending at index n is just 1 plus the max over all k that is less than n with values at index k less than values at the index n. Now we are ready for implementation, which is the final step. Implementing a dynamic programming solution is just a matter of solving subproblems in the appropriate order. What's most important is that before solving a particular subproblem, all the necessary prerequisite subproblems have been solved. In this problem, the order is actually fairly straightforward. We have to solve the subproblems from left to right. So let's now implement a function. Let's keep track of the lengths with a list. We can initialize all the lengths as 1 since every increasing subsequence will have at least one element. Then, for every index from 1 to the length of the input list, we will first find the necessary subproblems and then we update the length according to the generalization that we have specified. And then at the end, we return the maximum length over the entire list of lengths that we have just updated. There are many ways to implement this function, so don't get too bogged down in the details. The important thing to remember here is the thought process we use to identify and solve the subproblems in the right order. There's one last important question we should address. Everything we have done so far has been specifically with respect to finding the length of the longest increasing subsequence. But how do we actually find the underlying sequence? The key idea here is actually fairly simple. All we have to do is keep track of the previous indices for a particular subproblem. More specifically, if I solve the longest increasing subsequence ending at index I subproblem using the value of the longest increasing subsequence at index j, I can say that the previous index of index I is index j. Let's look at a specific example for some clarification. In this sequence, the previous index of index 0 can be labeled as -1 since there is no previous sequence value that leads to index 0. Same can be said about the previous index of index 1. For index 2, the previous index is either index 0 or index 1, and it doesn't really matter which one we choose since they both have the same length values. For the previous index at index 3, there's only one choice, index 1. Finally, index 4 actually only has one choice because the subproblem that's used to calculate the length at index 4 is the longest increasing subsequence ending at index 3, so the previous index is subsequently also 3. This type of pattern with tracking previous subproblems is a common trick used to solve dynamic programming problems. Let's now take a look at a more challenging problem. Here's the problem. You're given n boxes, each with a length, width, and height. Your goal is to find the height of the tallest possible stack of boxes with the constraint that a box can only be stacked on top of another if its length and width are both smaller. Another assumption that we will make to simplify things is that boxes cannot be rotated at any point during the process of stacking. So to make this more clear, let's take a look at a couple examples. Given the following set of 3 boxes, the answer to this problem is 6. The tallest possible stack is the green box on top of the blue box. Notice that we can't stack the red and green boxes on top of one another since it does not satisfy the constraint given in the problem. Now, as an exercise, given the following set of 6 boxes, see if you can figure out the solution for this input. I recommend pausing the video here and seeing if you can figure out the solution. Okay, so the solution in this case actually ends up being the following stack, with the red box at the bottom, orange box in the middle, and purple box on top. We can get a total height of 7, which is the best we can do. Make sure you take a second to verify that this is indeed the only solution to this problem for the given input. Alright, let's get started on trying to solve this problem. The first step, as before, is to visualize examples. A lot of times in dynamic programming type problems, there can be a lot of information thrown at you, and it's sometimes helpful to focus on one aspect of the problem at a time. When solving a problem like this, it might help to first visualize the particular constraint given for stacking boxes. After all, before we even figure out what's the tallest possible stack, it makes sense to first identify which boxes are able to be stacked on top of one another. Once again, the concept of directed acyclic graphs is really helpful here for visualization purposes. Let's connect a directed edge between two boxes if the box on the left can be stacked on top of the box on the right. Here's what the graph ends up looking like if we apply the constraints between all pairs of boxes. Now the nice thing about this representation is paths in this directed acyclic graph have a nice intuitive meaning. Every path in the graph corresponds to a stack of boxes. Now the goal is just to find the path that gives the greatest height. So now that we have a good way of visualizing the problem, our next step is to figure out an appropriate subproblem. This is another reason I love looking at directed acyclic representations of dynamic programming problems. If our final goal is to find the path with the tallest stack, it makes sense that partial paths should be a reasonable subproblem. What does a partial path represent? A path ending at a particular box, or a partial path, essentially means a stack where we force that box to be the base of the stack. Therefore, a subproblem that naturally arises from this idea is to find the best possible height of a stack of boxes with a given box forced to be at the bottom. This will allow us to find optimal partial paths in this graph, which will then build into the eventual optimal path. Here are some examples of instances of these subproblems. The subproblem in which the orange box is the base has a stack with a maximum height of 4. Another example is a subproblem ending at the yellow box in which the best possible height is 6. There are actually two different sets of stacks with heights of 6. The easiest one to see is the green box on top of the yellow box. And if we look at the subproblem that ends with the red box at the bottom, the optimal height is 7, which is also the tallest possible stack for the set of boxes we've seen. Take a second to make sure the formulation of the subproblem and how it works makes sense. The next step from here is to find relationships among subproblems. As we have done before, let's take a particular subproblem and ask what subproblems are needed to solve it. For example, if we want to find the optimal height of a stack of boxes ending at the red box, we have 3 boxes that directly lead to the red box. So the subproblems that are necessary are the optimal stack height ending at the orange box, which we already saw was 4, the optimal height of stacks ending at the blue box, which ended up being 3, and lastly the optimal stack ending at the purple box, which happens to only be 2 since no other box can be stacked on top of it. The next question is then, if we know the answers to these subproblems, how do we get the solution to the optimal height of stacks with the red box as the bottom? And the answer to this is actually fairly intuitive. We simply add the height of the red box to the maximum height of all the necessary subproblems. What's going on here is that we are taking our current subproblem, finding all the necessary prerequisite subproblems, picking the best one out of those, and adding the height of the current box to the best height so far. Let's generalize this relationship. Given a new set of boxes, let's ask ourselves, how do we solve the optimal height of a stack with the blue box as the base? There are 2 steps involved here. We first have to find the set of boxes that can actually be stacked above the blue box, and then the second step involves adding the height of the blue box to the tallest stack among all subproblems. We can use this relationship to now solve the subproblems one by one. The last piece of the puzzle involves the order to solve the subproblems. Order does matter. For example, if you want to solve the subproblem ending at the red box, we must first have the solution to the subproblem ending at the orange box. So the next question is then, How do we ensure a correct ordering if boxes are given to us in a completely random order? Well, we know that the boxes that can be stacked on top of each other are entirely dependent on the length and width of the boxes, with larger lengths and widths generally being able to have more boxes stacked on top of them. Therefore, a natural way to ensure we solve subproblems in the correct order is to first sort boxes by length or width. With this final piece in place, we are now ready to implement the solution. Given a list of boxes, we will first sort the boxes by their length. Just so we are clear, it doesn't matter if we sort them by length or width, either one works. Then, to organize a mapping between subproblems and their respective heights, we will construct a dictionary that maps each box to the tallest stack height possible, with that box as the base of the stack. We can initialize this dictionary with each box mapped to its own height. Then we iterate through indices from 1 to the number of boxes, select a specific box, and then find the set of boxes that can be stacked above the current box. We can define a helper function can be stacked, which will essentially do a quick check based on the given constraint. Now, following the general relationship that we have defined, the tallest stack with the current box as the base will be the sum of the current box height with the maximum height over the set of identified subproblems. After iterating through and solving all the subproblems, the tallest stack is simply the maximum height found amongst all subproblems. Again, this is just one of the many ways to solve the problem. The code for this problem has a lot of parts, so it's worth breaking it down to see how it really works. Given the example of boxes we've already seen many times, we first sort the boxes by the length, giving us the following order. We then define the dictionary mapping boxes to heights, which are currently set to each box's own height. Now, starting from index 1, we start with the subproblem with the purple box as the base of the stack. It's pretty clear to us that there are no valid boxes that can be stacked on top of the purple box, so the set of subproblems S is empty, and therefore the best height of the subproblem stays at 2, containing only the height of the purple box. We now move index I to equal 2, which corresponds to the orange box. Now we go through all the boxes before the orange box in our sorted list and find only one box that can be stacked on top of the orange box. Therefore, the answer to this subproblem for the tallest stack that can be created with the orange box as the base is the height of the orange box plus the height of the purple box, which ends up being 4. Moving to I equals 3, we now look at the subproblem ending at the blue box. Once again, the only valid box that can be stacked on top of the blue box is the purple box, so the height of the tallest stack with the blue box as the base is 3. Things get a little more interesting when we move to the subproblem with the yellow box forced to be the base. Now the possible boxes that can be stacked on top of the yellow box are the green box, the purple box, the orange box, and the blue box. The best height of all these subproblems is 4, so the height of the tallest possible stack with the yellow box as the base is 6. And finally, moving to the last index of I equals 5, which corresponds to the red box, the set of valid subproblems consists of the purple box, orange box, and the blue box. The best possible height from these subproblems comes from the stack ending at the orange box with the height of 4, so the answer to the subproblem involving the red box ends up being the height of the red box plus 4, which is 7. At this point, we have finished iterating, so we return the maximum height over all of subproblems, and that ends up being 7, so that is the final solution for this input. This problem at first looks pretty challenging, but following the steps greatly helped us narrow our focus and simplify the problem, and that's what ends up happening in a lot of dynamic programming problems. In many ways, the hardest part of dynamic programming problems is organizing the given information in the right way to identify the correct subproblem. That's the part that requires a lot of practice and creativity in problem solving. There is no doubt that finding the right subproblem can be the most challenging aspect of dynamic programming. I want to take a second to look at some of the most common subproblems you will encounter while solving these types of problems. The most common type is as follows. You're given an input sequence of length n, and the subproblem involves an ordered subsequence of length I, as shown here. This is exactly what was the case in the longest increasing subsequence problem. Another similar version of a problem like this that you might encounter is a sequence of length n, but given in a random order, where we first have to sort the sequence in the right order, and then the subproblem is an I-length subsequence. This is exactly the type of subproblem we encountered in the box stacking problem. Some other examples of common subproblems may involve the case where you're given two sequences and the subproblem involves the appropriate subsequences of each of these sequences. This is essentially a slightly more complex version of what we've seen already. A more unique type of subproblem may involve a sequence of inputs where the right subproblem is actually to expand from the middle of the sequence outwards. These types of subproblems are not as common as the other examples, but they are worth noting. Another important subproblem structure to be aware of is when you're given a two-dimensional array or matrix as an input, and the most common subproblem for this type of input is basically a submatrix of some dimension less than the input dimensions. These are the most common subproblems I've seen in my experience, and hopefully that will give you some direction when you're stuck in a particularly challenging dynamic programming problem. At the end of the day though, nothing beats practice and experience. The best way to improve your dynamic programming skills is through a lot of diligent work with problems and examples. That's all for this video, and thanks for watching. If you enjoyed the content, please hit the like button so that this content will be recommended to more people. If you want to see more content like this, please don't forget to hit the subscribe button. And if you want to more directly support the work of this channel, please check out the Patreon page linked in the description below. I'll see you all in the next video.